All right, up next is Dr. Rajesh Rajamani, Benjamin Y.H. Liu, and the TSI Applied Technology Chair of Mechanical Engineering at the University of Minnesota. He'll be discussing his project, Autonomous Vehicle Challenges for the U.S. Rural Midwest.
Okay, well, thank you all for coming. And I am Raj from the University of Minnesota. Everybody can hear me?
Put it closer to your mouth.
Put it closer? Okay. Okay, so I'll try to cover a couple of topics here. I'll describe some key challenges for autonomous vehicles to operate in rural environments. So, localization is one of the challenges. I'll talk about using GNSS and what are the challenges associated with accuracy and reliability of GNSS. And then I'll, show some performance using GNSS IMU Fusion for an autonomous vehicle. Okay, so first of all, rural crashes. First of all, about 75% of all roads in the U.S. are in rural areas. So about 3 million miles. Now, the risk of dying in a car crash is 62% higher on a rural road for a trip of the same length. So basically, there's a lot more risk of dying when you're on a rural road. Approximately 17,000 people are killed on rural roads every year. Another aspect is that intersections, although they make up a very small fraction of the roads, right? A lot of serious crashes happen at intersections. In the state of Minnesota, nearly 2/3 of all crashes that involve fatalities or serious injuries, they occur at rural intersections. So it's very important to address rural driving and rural intersections. What are the challenges for autonomous vehicles on rural roads? So, first of all, for steering control, as you all know, cameras are typically used in order to find the distance from the lane lines. So you measure the lateral distance to the lane lines using cameras, and then you use that as your feedback for steering control. Now, what happens on low volume rural roads, there might not really be any lane lines at all. There may not be lane boundaries. There may not even be center lines. So then how do you localize? So the traditional method of using cameras is really not usable on such roads. So, you can see this, this picture here showing you an example rural road with no lane lines. Besides this, there are, a lot of gravel roads in rural areas. So in Minnesota, we have over 70,000 miles of gravel roads. Almost 50% of the roads in Minnesota are gravel roads. So gravel roads, obviously, there are no lane lines. You need a completely different kind of localization method for steering control. Besides this, on gravel roads, there are a diversity of users. So you might have horse-driven buggies, agricultural vehicles, combine harvesters, and so you can have vehicles traveling at very different speeds and you need to go around them and so on. Also on gravel roads, what is not mentioned here, but on gravel roads, you can have, really large potholes, and, as a human driver, you would try to go around them. So, before the gravel road is raked and made good again, you can have very large potholes develop on gravel roads. Rural intersections, they can be missing signs. So as shown here on the picture here at the bottom right, rural intersections can be missing signs that indicate that there is basically, this is an intersection and you need to do something about it. Also in general, sensors for measuring cross traffic are not very good. It's really very difficult to measure vehicle trajectories on cross traffic and ensure safety. Here is another example of a problem, snow cover. So in the rural Midwest, you can have snow, and snow stays on the lane lines much longer than in the interior of the lane. So this is an example where this is a situation 2 hours after a snowfall, and you can see that snow is covering the lane lines, so the lane lines are not visible. Now the human driver can really see where the lane is, so it's not difficult for a human driver to drive here, but the steering control system really doesn't have a way to localize itself when the lane lines are missing. Okay, so then what would you do for localizing and doing steering control in such environments? What we're going to look at is high precision GPS, and I'll show you some of our work using high precision GPS. So we use GPS IMU fusion and RTK corrections. We'll talk a little bit about LiDAR maps as well. The other way to do this would be some kind of a system that replicates human driving. So human driving, even if you cannot see the lane lines, let's say you happen to be driving on a snow-covered road, you can still drive. Basically, you can essentially make sure that you're on the road, make sure that you're away from other vehicles, and you can still drive. And so you can try to develop these other kinds of driving methods as well without using actually precise localization. So that might be another option. Okay, so we'll talk about high precision GPS. This is the autonomous vehicle that we use for our research. It's called the MinCav vehicle. So this belongs to the Center for Transportation Studies at the University of Minnesota. It's a Chrysler Pacifica minivan. So it was put together for us by a vendor called DataSpeed that many of you might know about. It has a lot of very accurate sensors on it. It's got 3 Ouster LiDARs. So you can see some of the LiDARs here. This is one of the, so there is 3 different LiDARs on it. There are a lot of cameras. There is a forward-looking radar, a rear-facing radar, infrared sensors. There's a dual antenna GNSS system. So lot of very well instrumented. It's a very well instrumented car. There's also low-level software developed by DataSpeed. So there is it's based on a ROS system, and essentially they gave us software for doing acceleration tracking and steering angle tracking, and then some of the higher level control systems have been done by us. Okay, so this is the GNSS module, the Novatel module that we are using on the car. It's a dual antenna system, as you can see here. There is one on the left side of the car and one on the right side of the car. So by having 2 antennas, we can find not only the position of the car, but also the orientation of the car by having these 2 antennas. And then, GPS by itself has poor accuracy, right? You can only get accuracy of the order of 2 meters when you're driving. So that's certainly not the kind of accuracy that you can use for steering control. But what you can do is, that's more than enough for navigation. So all of us use GPS for navigation. So 1 or 2 meter error for navigation is not a problem at all. But for steering control, we need something much more accurate. So we use this RTK correction system called MinCourse that is available throughout the state in Minnesota. So essentially, they have receivers at over 140 locations in the state. And so the locations of these receivers are known very precisely. And so because of that, you can supply corrections. So these receiver locations receive GPS signals, and since their locations are exactly known, they can supply corrections to moving cars. And so then by using this RTK correction system, you can get centimeter level accuracy on a car. But we'll talk exactly about how accurate it is on the following slides. Okay. So satellite availability. These plots here show you how many satellites are typically available in various kinds of environments. So if you look at a rural road, so the bottom left here, you can see that you get, between 20 and 30 satellites are visible. So a lot of satellites are visible on a rural road. On a rural road, the advantage is you have open skies, good visibility to the satellites. So lots of satellites are visible. Downtown, on the other hand, so this upper left plot here, the number of satellites vary from 0 to 20. So there is like, 240 instances where 0 satellites were available, right? And so you can have very few satellites available. So there's, lots of tall buildings, so you get obstruction to satellite visibility. But there's also another problem in downtown. You get a problem called multipath. So multipath is where instead of directly receiving the signal from the satellite, you receive the signal after reflections from buildings. And because of that, you get a lot of error in localization. Another thing to touch on is that even though rural roads might have pretty good visibility, if you have tree cover, then you can run into some problems. So here on the bottom right is the suburban road. You have between 15 and 25 satellites available most of the time. On the other hand, on a road with tree cover, so this is basically West River Parkway. It's a very nice street in St. Paul. But here, we had a lot of trees, and so we had satellites dropping out and much fewer satellites available. So tree cover can again reduce visibility. So what happens because of obstructions and and in downtown and so on? The standard deviation of your accuracy can depend a lot on these factors. So rural road. So the left, I think you can't really see the mouse there, unfortunately. So, but basically the bottom left plot, rural road, the accuracy is always better than 10 centimeters, okay? Standard deviation, always better than 10 centimeters. Downtown, the accuracy can go to 1 meter or more for the standard deviation. So lots and lots of errors. Suburban road without trees, again, pretty good, mostly less than 10 centimeters in standard deviation. Suburban roads with trees, the accuracy goes down, so you get standard deviations of 30 centimeters, 40 centimeters, and so on, okay? This is the same for latitude. So I think you got a pretty good idea of what the problems are about GPS availability and accuracy on different kinds of roads. So downtown, it's going to be really very difficult to actually use GNSS by itself and do steering control. Rural areas with good visibility, open visibility to the sky, you're going to do pretty well, and trees are going to cause some problems. So what we do is we use GNSS IMU sensor fusion system. So an IMU, as you know, has accelerometers and gyroscopes. What you can do is you can use model-based integration. If you wanted to only use IMU system to localize yourself, you would be doing model-based integration of acceleration and angular rate signals. But when you have GNSS available, you can essentially construct an estimation algorithm that uses both GNSS and the IMU. And the advantage of having such a fusion system, and I can send you more details about the algorithms here, but basically the advantage of having this algorithm is that you get a much smoother signal. So if you look at it in the frequency domain on the right-hand side, you can see that the fusion system that uses both the IMU and the GNSS is much cleaner, has much less noise, and the raw GNSS by itself is much more noisy. On the left-hand side, this is not in the frequency domain. This is the real northeast position. And here, again, you can see that on a straight road, the fusion system is very nice and clean, very smooth. On the other hand, the GNSS signal by itself, the raw GNSS signal does jump around, and it is going to be a bit more noisy compared to the fusion system. So this is the advantage of the fusion system that we are using. Here is another plot that shows you what happens when you get a GPS outage. So this is driving on a street where there was a GPS outage for 4 seconds. So for 4 seconds, there was absolutely no GNSS signal. And in this plot, you can see that at one stage, the GPS signal jumps. Okay, I think I should try to use this here. Yeah, so at one stage, the GPS signal jumps, and then it just stays there because the GPS is not getting updated. But then eventually the GPS signal comes back, and so the GPS jumps from this point back to that point. And you can see that the IMU fusion system really works very well. So it gives you a nice, clean, smooth signal, and really hasn't drifted all that much, from the raw GPS. Okay, so a little bit more about, so what we've done is we've implemented this IMU fusion system with GNSS, and then we've implemented steering control. So I'll show you a video of our steering control system on the car based on GNSS. A couple of details here. So what we do is essentially we construct a desired trajectory for each road. So if you want to travel on a particular road, you need to construct a desired trajectory for it. What we do is we have multiple people drive on that road, and we combine the data from multiple drivers. We have an optimization procedure, and using that optimization procedure, we get a smooth trajectory, and we use that as the desired trajectory for the steering control system. And what this slide also shows you is how we calculate the lateral distance to the desired trajectory. So in other words, you need to find out how much off center you are from the desired trajectory, and then use that as the feedback. So this is the the calculation. This is how we find the lateral distance error, and we use that as the feedback. Sorry. And we use look-ahead errors. So we use not just the lateral position error, but we use look-ahead errors. So we use both the lateral error as well as the orientation error. So the orientation error we get because we have a dual antenna GNSS system. So we know the orientation of the car. We also know the orientation of the road because we have the desired trajectory for the road. So we can find the orientation error by using a combination of those two. We know the look-ahead error. The control system, for those of you who know about steering control systems, this is somewhat standard. This is what we use. So we use feedback, and we use what is called a lead compensator. For people who have a control system background, they'll be able to understand it. So we use a lead compensator. We use look-ahead error as feedback. When you're going on a straight road, that's all you need, a classical controller based on a lead compensator. But when you're going on a curve, you also need a feed-forward term. So you need to know what the curvature of that road is, and you need a feed-forward term in addition to the feedback term. So we have implemented all of these, a feed-forward and a feedback term. So this is the road on which we're going to show you a video on. It's basically Energy Park Drive, and this road has this is somewhat close to the university, so we do our testing here. It has a lot of very sharp curves, and you'll see that the system is 1 minute. Okay, so I'm really going to run out of time here. Let me just play the video. Oh. Okay. So the human driver is driving right now, but he's going to switch on the autonomous system. So he's switched on the autonomous system there, and you'll see that the system is, actually performs very well. It can go around sharp curves very reliably. If you're sitting in the car, you feel very comfortable. You don't. There's no roughness to the ride. It goes around very smoothly on curves, and some of these curves are pretty sharp curves. So I know I'm running out of time here, so let me stop the video and in terms of error, our error is of the order of plus or minus 5 centimeters on straight sections and at most 10 centimeters when going on sharp curves. So it's, it's pretty good in terms of accuracy. In terms of orientation angle, we have sub 1 degree error. So it's really good in terms of orientation error. So I was going to show you a couple of slides related to the use of LiDAR for localization. So I told you that under certain environments, GNSS might not work well because there might be tree cover and so on, right? It's certainly not going to work in urban environments, but even in rural environments, you might run into tree cover problems. So what would you do in those cases, right? We can try and use LiDAR. What I was going to show you in these couple of slides, I won't play those videos here, but what I was going to tell you is that in urban environments, you can use LiDAR and you can localize your vehicle quite well. So we are using an algorithm called Liu-TSI. It actually localizes quite well because it uses edges and planes as features for the localization, and so those are available in urban environments. Now in rural environments, it's very difficult to find such features. So in rural environments, when there is tree cover, you're only going to find trees. You're not going to find buildings, right? So it is very difficult to localize. So LiDAR localization has problems for rural environments. That is the message. So that brings me to the last slide, and I think hopefully you followed the whole talk and the conclusions are very clear. Camera-based lane line detection will not work on low-volume rural roads. You need other ways to localize. So we talked about GNSS IMU fusion. What are the challenges in various types of environments, downtown, rural with trees, rural without trees, and what is the possibility of LiDAR? How well can LiDAR work, right? So hopefully you got a pretty good idea of all the different aspects involved here. I think I'm running out of time, so I might not be able to answer questions here. Okay.
Please join me in thanking Professor Rajamani.